Hello, this is ISAT430, Materials and Manufacturing Processes. This is Lab 1, Sustainable Product Design. Alright, so today I'm going to talk about how to design product from the very beginning of the concept design into the prototyping and also put into production. You can see this outline. There are many topics we are going to go through. Today we're going to go through one by one. First, let's look at the product design process. So the whole process includes 6 major phases, from planning to concept development, system level design, detailed design, testing and refinement, and also production ramp up. First, planning means it's really the phase 0 at the very beginning. We need to know what kind of opportunities we want to design a product. Where is the market at, right? And also look at what is the objective, of this design. Basically, after this planning, you should come up with a mission statement. Show that what kind of concept or what kind of product you are about to design. Well, the next phase is concept development. After you know your mission statement, what is the general purpose of this product, then you will come to have a market analysis. For example, get to know what is the customer's needs, and also generate, based on the customer's feedback and needs, generate alternative concepts. And then you can screen the concept and find out different solutions or different product design alternatives, concept alternatives, and then you can put it into a system level design. All right, so after the concept has been identified, we'll start the system level design. System level design means we're gonna put different functions, make sure different functions can work together as a whole system. We call it defined product architecture, and also it decomposes of the product into many different subsystems and components. And in this phase, the idea is to make sure all these subsystems and functions components can work together. So the output of this system level design is a geometric layout of the product, and also functional specifications of each of the product subsystems, and a process flow diagram for the assembly process. Then after that, we'll come to the detailed design. So detailed design means we have to identify what are the materials, what are the geometries and tolerances for manufacturing, and also what are the standardized parts or some of the customer parts from the suppliers. So the output from this stage is the control documentation of drawings, computer files describing geometries and the toolings. So after we did detail the design specifications, then we'll start to make some prototypes. There are different types of the prototypes. Just give an introduction of the two simple ones. One is alpha prototype. So alpha prototype means they are prototype built with production intended parts. What does it mean? That means those are not from the production processes, right? They are not from the production line. Instead, those products can be made from many other different alternative process. For example, 3D printing, as long as I can make the product and to demonstrate how it works. Well, the beta prototype means they are built with parts supplied by the intended production processes. Right? So when I'm designing a product, I actually also designing for the manufacturing, know what kind of process need to go through, and beta prototypes are made from the production processes that is supposed to be in the manufacturing. So the goal of beta prototype is to answer questions about performance and reliability in order to identify necessary engineering changes for the final product, because eventually it will have to be made on the production line. And the lastly is the production ramp up. So the production ramp up means we have to train a workforce and also work out any problems in the production process. and also product at this stage sometimes supply to preferred customers and are carefully evaluated to identify any remaining flaws. A lot of times during the production ramp up stage, actually the product can be launched, means you can be released to the public. All right, so this is the 6 phases of product development. And now let's look at what are different types of product in product design. The first step is the generic products, which is market pool. Market pool means the product is there's a big market of the product, but there are a lot of variations. For example, sports goods, furniture, and tools. Right, so the team usually begins with a market opportunity and selects appropriate technologies to meet customer needs. There are a lot of opportunities in this big market. Then the team will have to just identify what kind of opportunity you want to pursue, and then to define what kind of product you want to make. Well, the next type of product is a technology push products. So technology push products means the team usually begins with a new technology and then finds some of the appropriate market. For example, touchscreen, a few years ago, right? When these technologies came out, people know that okay, actually this touchscreen technology can be used in many different applications. And then you just have to identify, okay, what kind of market do you want to go, and see what kind of product concept you want to come up with to pursue. So the technology push product. Another one is a platform products. So platform products means that new product will be built around established technological subsystems. For example, computer systems, right? You have an operational system, and you can develop software. You can develop or some many different apps, right? Same with consumer electronics, right? For example, the TVs, right? Or fridge or printers. They all have different different variation of the product design, but they have the same technology platform for the same product, same type of product. Another one is process intensive products. So this is this kind of product that is highly relied on the processes because their process is really unique. For example, food production and also some liquid or chemicals or pharmaceutical processes. These kind of processes are very unique. When you are designing a product, you have to know what kind of processes are available and all kind of what processes are associated with those products. So it's a process intensive products. Well, another type is customized products. So this kind of products, they have very slight variations of existing configurations. So, for example, motors, switches, and batteries containers, right? If you have a new product, then you probably just need to make sure that it meets the requirement of certain application. So there might be just a slight variation from other products. So there are customized products. Another type is high-risk products. So high-risk type product means those kind of technology or product concept have a lot of uncertainties. A lot of time actually high risk is also associated with high profit or high loss. Means probably what you have put the investment you have put in there will be all gone, or you probably get a lot of benefit out of it. So this why it's called high risk. And a lot of times a common products like this will be the pharmaceuticals, right? if you look at a lot of pharmaceutical companies, especially those kind of smaller ones, focus on research and development, and many of them actually will eventually fail. But some of them will survive and probably gonna get a good achievement. Another type is the quick build products. So quick build products are more like softwares and cellular phones. So the turnaround about this cycles about these products are very very fast. And so these kind of products can be rapidly made and also be tested by the customers or people, and then see if it works. If it does not work, then we'll just revise it and then test it again. So that's called quick build products. Another type is the complex systems. So complex system type products will be more like some jet engines, airplanes, automobiles. So all these kind of products have a lot of subsystems and components, and having all these subsystem components work together as a whole system requires a lot of work, and also requires a lot of validation and also integration. So that's why it's called complex systems. And all right, so these are the product types. So when you are trying to come up with a product concept or find a market, first you need to know that what kind of product type it is, because it will actually affect the product design process a little bit. All right, next let's look at the product development organizations. So suppose you're manager or CEO of the company, and then if you are designing a new product, there are different ways of the layout or organization of for the functions. For example, the first one is the functional organization. In this way, so a general manager basically manages three different functional managers. And functional managers mean each of the manager only manages one function, right? And so for this kind of functional organization, it has pros and cons. So the cons will be that, like, if there's a project, then it requires a lot of communication and coordination between functional managers. Sometimes it can be waste of resource and also energy and time to do those coordinations and also communications. Well, another type is a project organization. So for the product organization, so a general manager basically manages different project managers, and all these functions are organized in each of the projects. So people and resources are organized based on each of the project. A benefit of this kind of organization is that for some very dynamic, fast changing market, right? So the product can be very important. So it can easily adapt to the changing environment, and then come out with new solutions to a new product. So this is a project organization. But the cons will be, for different functions, probably there's less of a communication between different functions, and then they always has to work in the same team for different projects. So in order to deal with some of the issues with functional organization and the project organization, so people have come up with two other solutions. So it's more of a matrix organization. So matrix organization means that they're going to have managers not only in each of the function, but also with each of the managers, right? So for example, the two charts to the right, you can see that general manager basically manages either a functional manager or project managers, and also for each of the function they also have the managers. A good part of this is that their functions can be managed by functional managers, and also projects can be managed by project managers, and they can communicate well. we can communicate well on this. So this is the benefit of those kind of organizations. But also there are some of the problems. The problem will be that a lot of times, it's a lot of issues come out from people. So functional managers might sometimes have some kind of conflict or have some communication issues with project managers. They will have to prioritize what kind of duties. In this case, the general manager will have to be in charge and then tell or intervene into the situation. So that's different product development organizations. And then first, if we want to develop product, the first thing we need to have is opportunity identification, to identify what kind of opportunities for new products. And well, how to identify opportunities? There are different types of opportunities we can look at. The first one is Horizon 1 opportunities, which means it's very minor improvements or extensions of existing solution or existing product, right? We already have. So it does not have very innovative solutions or revolutionary product or function. So basically, it's pretty much the same as similar to the one we already have. So this Horizon 1 opportunity, only some improvement. While Horizon 2 opportunity means we already have the product, then we're gonna move to either we want to add another function or or some other major improvements with the prior compared to the prior product. So that's Horizon 2 opportunities. Usually it's the next generation, but still with the same core market we're good at. The next horizon will be the Horizon 3 opportunity. Means usually they develop a new solution for a totally new market, and then usually involves a lot of innovation and also a little bit high risk. For example, iPhone. Many years ago, when Apple first launched the iPhone, it's a new market, because right at that time there are not a lot of smartphones, and its design, its its product type is it's totally new product to the whole market and changes a lot of behaviors of customers. So this is a Horizon 3 opportunity. Well, after years, you can see iPhone has been constantly improving a little bit, mostly probably either at Horizon 1 or Horizon 2 opportunities looking at, because they are still at the same market. So this is the different types of opportunities you can look at. All right, so there is a process for identifying opportunities. The process includes establish a charter, generate a sense many opportunities, screening opportunities, develops promising opportunities, select exceptional opportunities, and then reflect on the result and the process. Let's look at the first one is establish a charter. The first step is establish a charter. So establish charter means we articulate goals and establish boundary conditions for our innovation effort. So similar to a mission statement, right? We want to keep it as very general in identifying opportunity. For example, what is the major market we do we want to get in, right? What kind of a service do we want to provide? Instead of giving too much details about what it should be, right? We just keep it at higher level. And then with that charter, we'll generate, in a sense, the different opportunities. And we can collect the information about it. And source of the opportunity can come from internally generated from our own employees, our own team members, or customers, right? We can have some surveys, customers. or competitive products. Look at the market and what kind of existing product we have. Sales force, from the sales, they can get, collect information what is hot or what is needed in the market. Also, university. So university also generate a lot of innovations. You can see what what kind of technology come out from research, and then look at what are opportunities. And sometimes there are independent inventors. They're also very innovative, so you can also collect information from them. Distribution partners as well, because they are close to the market, so we know what kind of what customers need from there. And then after we generate a lot of opportunities, we'll have to screen the opportunities. Right? We need to find out, okay, which opportunity do we want to pursue, while which opportunities do we want to get rid of, right? So basically, the goal of screening opportunities will be to eliminate opportunities that are highly unlikely to result in the create of value, and to focus on the opportunities worth of further investigation, right? Many different ways to screen opportunities. So either we can do a survey, right, to to list all these opportunities, and then do a survey, see which one have got most likes. And also we can do the workshop, right? To invite customers or people who will be using that to a workshop, and then have them discussions, and then collect their opinions or ideas about different opportunities, and then to screen them. So that's screen opportunities. And then after that, after we got one or several selected opportunities, then we'll develop some of the promising ones, right? So this one will be to resolve the greatest uncertainty surrounding each one at the lowest cost in time and money. So basically, select the one we want to want to pursue, or narrow down that. Then select exceptional opportunities. This stage is to further narrow down the scope. And there's the framework is called real win worth it framework. So basically, just ask some questions like, is there a real market and a real product? Can we win? Can our product or service be competitive? Can we succeed as a company, right? Or is it worth doing it, right? Is the return adequate and the risk acceptable? So by asking all these questions, they can further narrow down the scope, and then select the one or ones that you want to further to develop. Well, the last stage, reflect on the results and process. So basically, this is more of the feedback. You want to come back to the charter. Sometimes you see, okay, I might miss some opportunities. Maybe I should revise my charter a little bit. Maybe in my charter I kept the scope really too narrow. Or now maybe I can consider some other aspect of the market and see if we can get more opportunities for consideration. So that's a general process for identifying opportunities. Next is the product planning. So product planning means it is for coordination or organizing the resources and the time and the money, and also planning out the timing and for different projects of the products. So for product concept development, there are several activities we are involved in product concept development. The first one is identify customer needs. After we got a customer's needs, we'll establish some target specifications. We'll go through each one in details, but this is a general framework of product concept development, and this is a very important framework or the step product design. So after the established target specifications, we'll generate product concepts, and then select the one or a few product concepts, and then test those concepts, and then to design final specifications, right? And then after that you're probably going to do the prototype, and then to develop the final products. During all these processes, we also want to do the economic analysis, right? Benchmark competitive products, to look at what our existing products have, what do they have, and then how can we compare with those kind of products, and also build test models and prototypes. First of that process, first stage or activity of product concept development is identifying customer needs. For identifying customer needs, there's a method to do that, or steps, major 5 steps to do that. The first step is gather raw data from customers. Many different ways to gather data: interviews, focus group, or observe how others are using the product, or you can invite some lead users or extreme users, right? So the lead users means what are the typical users in the market, and also extreme users means when the user who will be using the product in an extreme environment, or extreme conditions, so they can test the boundaries or of the products, or tell the what is our requirements of the product in those conditions. And when you are conducting all these different activities to gather the raw data from customers, make sure you document all these interactions. There are different formats of documentation: the audio recording, or taking notes, or a video recording, or some of the photos. Can all be good information. Then after we gather the raw data or raw information, we'll have to interpret the raw data, because what customers will give you is some plain language, or maybe sometimes complaints, all right? Or you will have to convert that kind of raw data into the language that design engineers can use. And there are different guidelines for converting those kind of languages. For example, express a need in terms of what the product has to do, not in terms of it might do it, right? Express a need as specifically as the raw data, right? Or use positive, non-negative phrasing, or express a need that attribute of the product. And also avoid the words must and should, because if you are using must and should, means you are telling the design engineers what to do, right? What to do instead of what the customers need, right? So here we are only looking at need. In terms of what to do, we're gonna save that to the later stages of the product design. So there's the example of customer statements, and what is right and wrong. You can enlarge this picture on the slides when you are watching this video, and then to see different examples. And then next, after you interpret the raw data, we'll come to organize the needs, right? When I organize the data, and then write down what are the common needs from the customers. Sometimes several requirements or several customers' comments probably can be integrated, or can be combined into one need, right, into the product. So basically, just print and write each need statement on a separate card or self-stick note. Eliminate some redundant statements, right? Or group the cards according to a similarity of the needs they express. For each group, choose a label consider creating some super groups consisting of 2 to 5 groups, review and edit the organized needs of statements. So these are this is the guideline of how to organize the needs. Then after that, I'm going to establish the relative importance of the needs. Right, the customer might give you several needs or several requirements, but you will have to prioritize what are the needs are most important and what are needs are less important. You can come up with some weightings from experts or from surveys, and then to come up with a rank or a list of those needs. All right. So next is to come up with product specifications. So product specification is different with product requirements. Although sometimes product specifications is different with customer requirements, right? Customer requirement means that what the customer want to do. Or want from this product. Well, the product specification means it defines the product's the attribute of that, right? What the product it's a metric and the value. You can look at example. For example, the customer requirement saying that, well, the suspension is very easy to install. Should be easy to install. Well, the product specification in this case, you have to convert it to a more engineering language. You can say the average time to assemble the fork to the frame is less than seconds, right? So this is why you have to convert customer requirements language into engineering language to this product specification. So each of the specifications should consist of the metric and of the value. Right? So the metric in this example is the average time, right, to assemble the fork and the frame, while the value will be the 75 seconds. So this is how to convert the customer requirement to specifications. So for converting those specifications, there's usually you can come out with a big chart to organize all these metrics, and also come out with the values to each of the metrics, and those kind of tables or charts it varies, but there are typical ones. For example, house quality is one. So basically, you list all the customer requirements, and then based on these requirements, it coordinates with different metrics, right? Different metrics, and then for each of the metrics, you can come up with values in it. And then you can see how the metrics or the specifications matches or meets the customer requirements. So this is the house of quality. And you can see in examples of house quality and another table to add in the 2 pictures. You have to enlarge the pictures to see all these examples. Next, after we come up with the specifications, we can come up with different concepts, right? So a product concept is now appropriate a description of the technology, working principles, and form a product. It's a concise description of how the product will satisfy the customer's needs. Because we already have all these specifications, we know that what the customers need in this product. So now we need to define the product concept. Okay. So for defining or generating product concept, there's a 5-step method. So the step 1 is to clarify the problem, basically to understand what kind of say functions or solutions this kind of product is providing, right? It might include different sub problems, right? And then you search externally or internally what are the concepts, what are the ideas, right? It can be lead users, experts, patterns, literature, or benchmarking. Internal research, it can be individuals, team members or the group. And then after we collect all these concepts, existing concept and new concept, we'll have to explore systematically to for example, come up with combination table. You can see one example of the combination table at the bottom left corner here. This is for handheld nailer or hand gun for nails. So you can see there are different solutions, right, for each of the requirement. Right, there's a convert. We need to first convert electrical energy to translational energy. Then there are different solutions. Either you can use the linear motor, or solenoid, railgun, or rotary motor with transmission. Right, there are different solutions, and also accumulate energy. It can be a spring, right? Spring system works, and also moving mass also works. The last one will be applied translational energy to a nail. Then it can be a single impact or multiple impacts or push nails. There are different ways. So after we come up with all these different solutions, we can generate different concepts for the product design. All right, now once you have different product design concepts, next thing is to select concept. So this is the one example for concept selection. For example, they are designing a reusable outpatient syringe, right? So the reusable outpatient syringe, it come up with seven alternatives or seven concepts. They're all drawing here. Now the next job is, how do we find out, what kind of concept should we pursue, or should we have further investigation? For concept selection, people all have their different methods, or have used their own methods to choose concept. Either we find experts from external decision, or product champion, right? Or totally by our intuition. Sometimes we can also do voting or surveys, or just simply list the pros and cons, or we can do just do a prototype and then test it and then do it again and then see which one works, or we can do the decision matrix. Right, all these kind of methods work in some way, but it's better to have a structured method so we do not miss anything. So a structured method will be including 6 steps. The first one is prepare the selection matrix. So selection matrix means we first need to identify what are the criteria for selection, right? Find out all the different criteria, and then have all different concepts. You can come up with a matrix. The next one is to rate the concepts. Right, you probably need to give the weights for each of the criteria, and then give the scores for each of the concept with corresponding to each of the criteria. Then after we got all the scores, we're gonna rank the concepts, and then after you rank the concepts, then you're probably gonna find out some highly ranked concept. Something to note is that we do not have to only stick to one concept, because sometimes you can find out a combination or combining 2 or 3 concepts in together probably can become a better concept. So this is the next step, was to combine and improve the concept. And then next will be to select one or more concept you want to have further investigation. So an example of the rating of the or rank of the concept can be seen in the figure here. All right. After that, we'll do some of the concept testing. So concept testing means we want to see which one works or which one will not work, right? Some of the questions you can ask include which of the several concepts should be pursued, how can the concept be improved, how many units are likely to be sold, and also should the development be continued. So this is define the purpose of the concept test. The next is to choose our survey population. So survey population means it's better to represent the target market. For example, for this scooter, right? Usually the scooter are used by either college students or some urban commuters. So when you are looking for the population of this survey, you probably want to send it to people from largely from those two groups. Right. And also, you want to make sure the sample size is large enough so your data can actually represent the market. Then next, you can choose a different survey format. Some of the survey can be face-to-face. Some of the survey can be telephone or postal mail or electronic mail or some internet surveys. So in the surveys, you will also one function or one purpose is to communicate the concept. Many different ways to communicate concept. You can see all these pictures. You can either draw a sketch, sketch of the product, or you can have some of the renderings, and or storyboard. All right. We learned about storyboarding in 331. You probably already made some of the storyboard yourself. Storyboard actually conveys a very good idea about products. Also, the video and working prototype also works. Right. So next one is to measure customers' response. So after you communicate the concept to the customers, then you have to see, what are the customers' reactions on those. Some of the responses can be definitely would buy it, or probably will buy it, or might not buy it, or probably would not buy, or definitely would not buy. So those kind of different concept testing strategies that you can use. All right. So after we select the concept, then next stage or next phase, of the 6 phases of product design is the product architecture. Well, first we need to understand what is product architecture. There are several definitions or terms we need to understand here. Well, first is the physical element. So physical element of the product is the parts, components, and or sub-assemblies that ultimately implement the product's functions. Right? These are physical components. Something we can see it here. Functional elements means individual operational transformations that contribute to the overall performance of the product. So basically, what are the functions of the do we need for this product, right? What are the functions? For example, like a printer, right? It should be print. It should move the papers, right? It should be able to do some controls at control panel. So these are the functional elements. Another concept is another term is chunks. So chunks means the physical elements of the product are typically organized into several major physical building blocks, right? So those kind of chunks are basically these kind of building blocks with several with different functions. And the architecture or product architecture, so it's a scheme by which the functional elements of the product are arranged into physical chunks by which the chunks interact, right? So basically the functional elements are in the physical element, right? Organized or arranged in the physical chunks. So this is a product architecture, right? How the functions are embedded into the physical components. So basically this is the product architecture. Another term is a modular architecture. So the modular architecture means it has two properties. So that's a chunk implement one or a few functional elements in their entirety. Or the another one is the interactions between the chunks are well defined and are generally fundamental to the primary functions of the product. Right. For example, let's look at the picture at the bottom right corner. So this is our presents two models of bicycle brake and shifting controls. You can see the left one is a module architecture. Means the two are separate, right? So the brake and also the shifting control are separate. Well, the second, the one to the right is integral architecture. Means they have all functions into one module. So this is a modular architecture. Well, different types of modularity. One is a slot modular architecture. So for this slot modular architecture, is each of the interfaces between chunks in a slot modular architecture is of a different type from the others, so that various chunks in the product cannot be interchanged. So example will be the automobile radio, right? So in the car, there's the one specific or unique, right? There's a unique model just for the it's just for the radio, and it can be changed to another radio set, but it cannot be changed to some other kind of functions, right? So it's just specific for this radio function. So this is a slot module architecture. Another one is a bus modular architecture. So bus modular architecture means there's a common bus or a common physical component that which other chunks connect via the same type of interface. You can see this picture. And some examples are like traffic lightings, shelving system with rails. You can see some pictures there, and also the the roof racks of the cars. Right, you can slide things on it, and so that's more bus modular architecture. Well, another one is the sectional modular architecture. So sectional means that all interfaces are in the same time, but there's no single element to which all the other chunks attach. Or compared to the other two, you can see there's always one single element that other components are attached to it. But for the sectional modular architecture, it's not the case. They can always have interface between each other, right? So some examples would be like office partitions or sectional sofas. You can move it here and there, and also interface. Next is establishing the architecture. So how to establish the architecture? There are several steps. The first, we want to create a schematic of the product. So the schematic is a diagram, so basically representing the team's understanding of the constituent elements of the product. You can see here in the diagram, you need to list all the functions, right? List all the functions and the physical components of the product, and also to show how they flows and how they connect to each other. So this is the schematic of the product. And then after you have this this diagram, I'm gonna convert it to, or cluster, right? Cluster the elements, some of the elements into chunks, right? To chunks. For example, here is a guideline how to assign each of the elements of the schema to a chunk. Geometric integration and precision, right? Now function sharing, or capability of vendors, or similarity of design, or production technology, or localization of change, accommodation varieties, enable standardization, or portability and interfaces. So these are different ways that you can cluster those kind of elements of the schematic. Then after that, we'll come up with a rough geometric layout, right? We know how different chunks of the functions, with physical properties or physical elements are, and then how do they gonna interact as a physical product. So we have to create a geometric layout. So the layout can be created in either 2 or 3 dimensions. You can use drawings or computer models or some physical models as well. So you can see some examples of a printer, right? There are different functions of those. Printing cartridge, the paper tray, right? The printing mechanism, user interface, logic board, are all these different chunks, and you can see you can come up with some similar layouts. The last step is identify the fundamental and incidental interactions. So the fundamental interactions means the lines or the connection of the chunks with each other. So that's fundamental interaction. While incidental interaction means those kind of interactions are not from the direct contact. Instead, it's from certain function elements. For example, the vibrations caused by the actuators of the paper tray could interfere with the precise location of the print cartridge in the x-axis. So this kind of interactions is not direct contact. Instead, it's from the other functions of the parts of elements. So that's fundamental interaction and also incidental interaction. You need to identify those, right? All right. Next one is the delayed differentiation. So usually a company offers many different types of the product, and it has different variations. And so postponing the differentiation of the product until late in the supply chain usually is called delayed differentiation or simple postponement. So why do we want to do that? Well, let's first look at the difference by looking at the 2 pictures. Well, to the left picture, early differentiation means, for example, if it is a seat, all right, we're gonna combine or we can assemble all the seats at the factory, and then we send all these assembled seats to the customers, right? Well, the postponement means, well, for the seats, at the factory, we're gonna have a partial assembly, so not assemble everything. We do not assemble everything, and then instead we're gonna leave some of the sub-assemblies to the end of the supply chain, or to the distributors, right? Or the inventory, where it is hold. For example, if ABC are different companies, different countries, and they only have different packages, in different languages. Well, in this case, if we are doing that at a factory, which means that the factory probably have to hold a lot of inventory of these packages, and also because the company is not sure what is the quantity of the products will be purchased by the customers from each of the destinations. So the factory is actually experiencing a lot of risk and also inefficiencies of having all those customizations or differentiations in the factory. Instead, if the factory can send all the same parts or the same products to all the different destinations, well, the only leaving the last stage, that is put the package in it on it, right? So in this case, it saved a lot of resource, time, and energy for the company, and also actually increases the efficiency of the distributors as well. So the distributor do not have to store a lot of inventory. Well, there are two design principles for delay differentiation. The first one is the differentiating elements of the product must be concentrated in one or a few chunks. You can see this example. Design A, for example, for a printer or for any kind of electronic device or equipment. Well, the U.S. and Europe, or in some Asian countries, they are using different voltages, right? Well, in this case, for the power, they will have to have some adaptations or have some variations of the power. Well, for the first design, you can see, the power cord is actually embedded into the equipment itself. It's enclosed. You have the traces and logic board, and if you want to do the customization of the power, then there's a lot of work that's involved in the assembly, right? There's a lot of differentiation in the assembly. Same, it will increase the time of assembly. It will also increase the complexity of assembly. Well, instead, the design B, so the power supply is confined to the cord and the power supply brick. So basically, this is only one chunk that is different with for different product types. Well, in this case, you can see this whole device or equipment are all the same. For the assembly line, they only need to assemble all the same products, so it's really efficient. And the only difference is the kind of power cord. The power cord, they can just differentiate at the end of the production process. So this also saves time and energy. So that's why differentiating elements of the product must be concentrated in one or a few chunks. It will save time. Another one is the product and the production process must be designed so that the differentiating chunks can be added to the product near the end of supply chain, right? Like I explained before, package differences at a distributor instead of the factory, right? All right. Next, let's look at the platform planning. So platform planning means it's a collection of assets, including the component designs shared by these products. So you can see for the printer, right? You can see there are different attributes like a black print quality, color print quality, print speed, footprint, the paper storage style, right? They all can be different models, right? They all can be different models. And also their families. For example, near laser quality is 300 dpi, and our near photos quality, 100 sheets, consumer, USB, parallel port, all of those. So it's more like you have to find out different configurations, and then you group them in different models, right? As a company, you can predefine all these models by yourself. Well, I think what is the trend right now, for example, when you are purchasing computers, you can actually find your own configurations as in just to get your own, the one you just needed, right? So this is a product platform, how you can group or find a differentiation plan for products. It depends on the attributes of the product. Well, next, so after you come up with the concept, and then have this kind of product architecture, we can do some industrial design. So the industrial design is a professional service of creating and developing concepts and specifications that optimize the function, value, and appearance of products and systems for mutual benefit of both users and manufacturer. Well, the product design itself mainly deals with functions and technology and meeting the customer requirements. For the key functions. Well, the industrial design mainly deals with how this kind of product can actually increase, have this usability and also appearance, and also with low cost for manufacturing. Right, so this is the industrial design, and there are several critical goals for industrial design. Utility means the product's human interfaces should be safe, easy to use, and intuitive. Each feature should be shaped so that it communicates its functions to the user. So basic ergonomics, right? We learn about ergonomics in 331. And all these visions, the colors, and also the principles of design can all be applied to this. Another goal for industrial design is appearance. So basically, the appearance should be able to attract customers, right? And also another goal is to ease of maintenance. The product must also be designed to communicate how they are to be maintained and repaired. Of course, low cost, form and feature have a large impact on the cooling and production costs, so these must be considered jointly by the team. Communication in product design should communicate the corporate design philosophy and missions through the visual qualities of the products. Right, a lot of time you can see the products have different themes, and it represents the brand. Right, for example, Apple products you can see have a common theme. Right, Microsoft they have another theme. So this is all. This is some of the goals for industrial design. And two major needs for industrial. The reason that we need industrial design is ergonomic needs and also aesthetic needs, right? You can see an example of industrial design for the Apple's mouse, how it evolved, how the changes is kind of from the very first model to the latest model. You can see aesthetic wise, and also ergonomic wise. How it has been improved by this. Something to mention that I think the Apple company really is a good example of adoption of industrial design. Actually, it fundamentally changed the company because I remember a lot of years ago, the smartphone is not actually innovation from the Apple. At that time, there are already some of the smartphones on the market, but Apple did the best job because it implemented a really good industrial design, so the increased the usability of the customers and the interface really attracts people. So that's why it achieved such a big success, at the beginning, for phones. All right. So for industrial design, actually, industrial designers have been usually, of course, depends on the products. And for some of the user-driven products, for example, involves a lot of users' experience. Usually, the industrial design engineers or designers usually have to be involved at the very early stage from the concept development. Well, if it is for technology-driven products, the first few stages are actually a bit more of a technology or for concept development, but industrial designers can also be involved at the end of the concept testing and also system level design, and then all the rest of stages in production. So this is how it's where or when this industrial design must involvement in this kind of product design stages. Well, how do we assess the quality of industrial design? Fab aspects, the quality of user interface, right? Emotional appeal, ability to maintain and repair the product, and also appropriate use of resources and product differentiation, right? So the quality of the user interface means does the features of the product effectively communicate their operation to the user, or is the product's use intuitive, or are all features actually safe, have all potential users and uses of the product have been considered, right? Well, for the emotional appeal, some of the questions you can ask include is the product attractive? It is exciting to the users. Does the product express quality? And what images come to mind when viewing it, right? And does the product inspire pride of ownership? Right? Does the product evoke feelings of pride among the development team and the sales staff? Next one is the ability to maintain and repair the product. Is the maintenance of the product obvious? It is easy, or do product features effectively communicate assembly and assembly procedures? Also, you can look through the rest of those questions for the other two steps, two metrics, right? For the use of resources and product differentiation. All right, next topic is design for environment. So after we did the industrial design, we also have to think about what about the sustainability, right? One thing is life cycle thinking. So sustainability means, or environment means the emissions, right, or the pollutions, or the resource use and the energy use involved in, and not only in the product materials itself, but also involved in manufacturing, in distribution, in use, and also the disposal of the product. You can see this is product life cycle. So it's a life cycle. So that's why when we are looking at a product environment, the environmental impact of the products, we also need to think about the whole life cycle of the product. So life cycle thinking can be very important. So there's a video in this link. So if you are watching this video, make sure you click the link and in the slides, and then finish this video before we move to the next slides. All right, so the key areas for design for environment includes the materials, chemistry. For example, because the materials are the main source of physical components for the emissions, right? And also the disassembly. If it is, for example, if it's a whole part. If something is not working, you probably have to just abandon the whole thing. But if the product is made of different samples, sub-assemblies, you can probably gonna reuse or recycle some of the components, good components. So disassembly, and also recyclability. Some of the components of the parts can be recycled, and you can design in that when you are designing the product itself. For example, choosing a different materials that can be recycled, or choose a certain component that can be made of recycled materials, right? A method to evaluate the environmental impact of the product is life cycle assessment. We talk about this in 330. It includes goal and scope definition, life cycle inventory, impact assessment, and interpretation. And also, I discussed two examples of a life cycle assessment. One is paperbacks, and the other one is life cycle LCA on Honda Civic car. If you don't remember, you can go back to the 330 slides and look at how life cycle assessment was conducted. Some of the guidelines for design for environment, they can organize as goals and ranges. So for example, the materials, you can reduce the use of raw materials, right? Instead of using a lot of material, think of where are the components or where are the parts that you can reduce the use of it. And also choose plentiful renewable raw materials instead of material that cannot be recycled, right? Eliminate toxic materials, increase the energy efficiency of material extraction processes, reduce discards and waste, and also increase the use of recovered and recycled materials, right? So that's all at the materials part. Select more of a selection of materials. So next stage is the production. So production is how can we reduce the energy that consumed in the production stage, and also reduce the materials that are involved in processing of the parts, right? Then it's a distribution. So distribution is we can find with the most energy efficient shipping, reduce emissions from transport, and eliminate toxic and dangerous packaging materials, and eliminate some or reuse packaging, right? And the use stage, we can extend useful product life, secondhand use of products. Promote the use of product under the intended conditions to make sure it's always be maintained in a good quality or extend its life. And enable clean and efficient servicing operations, and also eliminate emissions and reduce energy consumption during use. For example, the cars, right? The air conditioners, fridge, all these energy-consuming products. Recover. So some facilitate the product disassemblies to separate materials. There's a design for remanufacturing or design for assembly. Right, so you can always when you are designing a product, you have to design it something can be easily disassembled, and also enable the recovery and remanufacturing of components, facilitate material cycling, and reduce waste volume for incineration and landfill deposits, because incineration and landfill are usually generate much more emissions than other means of waste treatment. All right, next is design for manufacturing. We also have to look at how this can design are related to the manufacturing itself. A couple of concepts here. So design for X and design for manufacturing. Design for X mean design really means many different features such as the manufacturing ability, variability, and the cost, yield, reliability, many different attributes. So we are so that's why people call it design for X. While design for manufacturing is more specifically related to the manufacturing itself. Basically, it's a general engineering practice of designing products in such a way that they are easy to manufacture. And design for manufacturing actually closely related to manufacturing costs, because the reason I want to do that is to eliminate the cost for manufacturing, and also make sure the manufacturing have the good quality, okay, or can be easily manufactured. So that's why design for manufacturing really requires a cross-functional team, because it needs knowledge of both the design and also manufacturing as well as management, right? So the 5 steps to do design for manufacturing, one is eliminating the manufacturing cost, reduce the cost of components, reduce the cost of assemblies, reduce the cost of supporting production, and also consider the impact of the design for manufacturing decision on other factors. Then next, I'm gonna talk about it one by one. Well, estimating the manufacturing costs. Here is a chart to look at how the manufacturing costs are actually calculated or can be decomposed of. There are materials, right? Like components itself, it has a cost, and also assembly and also overhead. Assembly means more of a human resource, the time involved in assembly, and also energies and also toolings. While the overhead means more about supporting functions of the production. In 330, we talk about how do you categorize the costs, right? Direct costs, indirect costs, support overhead costs. What do they mean? All right, so this is how you can estimate the manufacturing cost, and it can be organized based on a bill of material. So this is a chart based on bill of material. You can see for each of the components, you can you can categorize what kind of the costs are actually associated with each of the components. Like purchase material, or assemblies, processing, tools, all of those things. Then you can add it all together, find out what is the overhead cost, what the charges, and then find out what is the total cost for each of the components. So this is one way to calculate manufacturing costs using bill of materials. Also, some of the guidelines to reduce the cost of components is to understand the process constraints and the cost drivers. This means that this is to say that some of the processes really are high cost. For example, if you are giving a tight tolerance, sometimes you probably have to use a totally different machine or equipment or operation to make it. While in this case, the process will be a constraint, and you probably have to increase a lot of cost just to change a little bit of the tolerance. So this is why you need to understand the process constraints and the cost drivers. Where are these costs are to process those. And the next one is redesign components to eliminate processing steps. So if you can make several components into one integrated parts, it actually eliminated processing steps. So it means you are eliminating machines or a human resource and all, as well as time for making it. So that's also the same saving the money. Next is choose the appropriate economic scale for the part process. So this is more for the manufacturing. We are looking at more the batch production, or we are producing high amount of products or parts, right? What strategies of what kind of components design will be better for those large scale of part processings. And next one is the standardized components and processes. If you can use the standardized components, means you are using less variations in tools and also processing operations as well. So that's also a saving of standard time. Means there's less of change or setup times for different configurations. Next one is reduce the cost of assembly. So because assembly is also has a lot of costs related to it, so if you can reduce the assembly steps, means you are actually reducing the cost, right? So one way is to use the integrated parts, as I just mentioned, using one whole part or combining of the several sub-assemblies. In this case, integrated parts do not have to be assembled. And also, integrated parts are often less expensive to fabricate than the separated parts they replace. For example, a big chunk of the frame, it can be casted, right, with one single part, instead of having multiple parts made from multiple processes and then assembled together, right? So there's a concept it's called design for assembly. So design assembly means you design the product or design the parts that can be easily for assembly processes, right? Or you can reduce the cost for assembly. Some of the guidelines will be the part inserted from top of assembly, part is self-aligning, part does not need to be rendered, it requires only one hand for assembly and requires no tools, is assembled in a single linear motion and secured immediately upon insertion. So these kind of guidelines will actually what I will talk about in our course of the joining lecture, which is the last lecture of this course. And there's we're gonna want to talk more about different assemblies and also how to design parts and products for assemblies. All right, so another guideline is to reduce the cost of supporting production, right? So the supporting production of supporting some of the supporting functions include inventory management, supervision, and also human resource management. So if the system is complex, means you probably have to deal with this a lot. But if the manufacturing system is a little bit simple, well, in this case, actually, it will save the resources, save the time, and save the supervision. Right, so that's why there's a concept of people have been trying to make the manufacturing more simple instead of having a lot of complexity. Right. For example, Tesla Model Y recently they have announced that they will make the whole body frame as one part instead of having a lot of parts assembled together or welded or assembled together. They want to have to do with the one casting of the frame. So this is also one way to simplify the manufacturing complexity. For arrow proofing, the same thing. If there's some arrows, actually you are increasing the cost. So there are always some ways to identify the failures and other proof. Come out with some solutions to do some arrow proofing. So FMEA, failure mode effect analysis. And we did that in 331. So you should be able to, familiar with FMEA. You can also use this method to to identify what are the risks, what are the failure modes for the parts and products. Well, lastly, for the design of manufacturing is to consider the impact of design for manufacturing decisions and other factors. Because design for manufacturing itself, it's an activity, right? It also takes some time, and sometimes the design for manufacturing also involves purchasing of new equipment and also purchasing new materials or toolings. So there's an investment in it. So you have to think about how this kind of investment will affect other activities in the product design, right? Last step is prototyping. So after we got everything, we identified the concept, right? We did the product architecture. We come up with specifications. We did we have detailed design, right? We also have design for manufacturing. Now we need to come up with a prototype, right? To test it. So there are different types of prototypes. One is a physical prototype. For physical prototype means they're tangible. They're artifacts created from appropriate to appropriate the product basically these are something we can see normally. Well, another prototype is an analytical prototype. Those are non-tangible, usually the mathematical or visual manners, right? A lot of times they are 3D models, or in computer simulations. Also, another way to categorize the prototype is by comprehensive prototype and also focused prototype. So comprehensive prototype means the product the product you made that actually includes almost all, if not all, at least most of those attributes of product, right? Well, the focused means we're only prototyping one or very few attributes of the product. You can look at some examples here. So this is one example. You can see there's a look-like a prototype. It's called a focused prototype, right? So this is basically the appearance, what it look like as the whole product, and also there's the works like. So works like basically only simulates or it only prototypes the function of a part of the product. So for example, in this case, it's a wheel, right? It is only testing the wheel. So this is the works like and versus the looks like. A lot of times, if you are using focused prototype, you're gonna do both the looks like prototype and works like prototype. Combining of the two give users or give customers a better representation of what it is. Well, a complete system will be like the picture is showing here. For analytical prototype, you can see it's a 3D CAD models. To the right, there are two pictures of the city. These are analytical prototypes. Well, why we are doing prototypes, right? The most important part is the learning, to see if our design actually works, right? If our design actually meet the customer requirements or customer needs. Another one is to, if we have prototype, can communicate, right? Communicate our ideas, our concept, or our design to other people, including the top management, the vendors, partners, team members, customers, and investors, right? Also, one purpose of the prototype is integration, to make sure that we design different functions, different components. When we put them together into a system, if they will work as expected, right? To test it and then to see if it works well. Of course, the prototype also signifies the product design actually reaches a milestone, right? It demonstrates that product has achieved a desired level of functionality, and also it provides tangible goals, demonstrate progress, and also serve to enforce the schedule. Different prototyping technologies, 3D models, CAD CAM models, you can all use for analysis and also to draw. Another type is 3D printing, right? So it has been very popular in recent years. You can 3D print a part or a product and then to communicate your ideas or concept to others. All right, so that's all for today. And so basically we talk about the whole process of the product design, and also what are different considerations like design for manufacturing, design for environment. And just keep in mind when you are designing a product, if you are sticking to this kind of environment, to this the guideline or to this process, usually you will not miss any kind of important steps or miss any important points that in product design.